So far with motion, all our formulas have been in terms of time, or t. Because that's the basic, I guess, two-unit idea. It restricts the type of problem that we look at. If we can look at velocity and acceleration in terms of actually the displacement rather than the time, it just opens up a whole heap of other stuff we can look at. So velocity is some function of displacement rather than some function of time. Okay. What we can say is acceleration. Now the big mistake is people just differentiate velocity to get acceleration. That's true when it's with respect to time. But when it's with respect to displacement, it's not true. You actually have to differentiate a half v squared with respect to displacement. Let's prove that. Okay. So acceleration is dv to t, so the derivative with respect to time. But I could rewrite dv to t as dv dx times dx to t. Well, dx to t is velocity. So now I've just got dv dx times the velocity. Okay, I'm now going to rewrite velocity. Instead of just calling it v, I'm going to call it d dv of a half v squared. Because if you were to differentiate a half v squared with respect to velocity, you would get v. Well, the dv's, if you like, now cancel, and we get our d dx of a half v squared. So there's the proof of our relationship there. So, okay, what we've now got is a problem where acceleration has now been quoted in terms of its displacement rather than time. We're going to find its velocity in terms of displacement again, and then we're going to, they've given us some initial conditions to work with. We know that velocity is 2 when displacement is 1. Right, acceleration's in terms of displacement, so I use d dx of a half v squared rather than dv to t. So a half v squared, to undo the d dx, if you like, we integrate. So I get 3x minus x squared plus some constant. We know that when x is equal to 1, velocity is equal to 2. Sub in, we get our constant, turns out to be 0 in this case. And so there's an equation, not for velocity, but for velocity squared. Well, they want an expression for velocity. So velocity will be plus or minus the square root of 6x minus 2x squared. Now, this is the first problem some people have to come to grips with, because you're thinking, well, hang on a sec, how can I have two velocities? It's not possible for something to have two velocities. And that's because we're not dealing with respect to time anymore. Certainly at a particular time, you can't have two velocities. But at a particular position, you can, because they would be at different times. At one time, I might be here, but travelling towards the wall, but at another time, I might be at that same position, but travelling the other way. So it is possible for a displacement to have two different velocities. Okay, a couple of things to note. This helps us work out the path of the particle, because we know v squared is always going to be greater than or equal to 0. Or another way of saying it, whatever's under the square root sign must always be greater than or equal to 0. And that's in terms of displacement. So we can actually work out where the particle is captured, in what sort of path. So in this case, 6x minus 2x squared will always be greater than or equal to 0. We've got just a quadratic inequality to solve, which is between 0 and 3. So our poor little particle has a very, well, boring life. It just goes between 0 and 3. And that's all it can ever go to. It can't go anywhere else. All right, here's another one. Acceleration is 3x squared. Initially, we're going to start at 1 unit to the right of the origin, travelling with a velocity of root 2 meters per second, but it's going to be in the negative direction. We're going to find actually displacement in terms of time, even though my initial equation is in terms of displacement. So again, it's in terms of displacement, so d dx of a half v squared would be acceleration. So a half v squared will be x cubed plus a constant. Sub in my initial conditions that they told me. Well, they told me when t equals 0. Well, that's not much use right now. But they also told me that x equals 1, v equals minus root 2. I can use those two conditions. Oh, how lucky am I? That constant just keeps working out to be 0. Nice numbers. So velocity squared is 2x cubed. So velocity is plus or minus the square root of 2x cubed. Well, velocity is dx to t. And it's in terms of displacement. So now I can get a link between displacement and time. But there's one thing you might notice. I've only written down minus the square root of 2x cubed, not plus or minus. See, when I change it from velocity to dx to t, I have to make a choice. Which one am I going to integrate? Am I going to integrate the plus the square root or the minus the square root? I chose the minus. Why? Yeah. See, I've got initial conditions that they told me. And they told me that when x equals 1, v equals minus root 2. So therefore, when I sub in 1 into this problem, I need to get the answer minus root 2. So it's minus root 2, x to the 3 on 2. But it's in terms of displacement, so I'm going to turn it upside down. So the t dx, but now the power is going to be minus 3 on 2, and I've got minus 1 on root 2. So the t dx, so to get t, we shall integrate. So t now ends up being the square root of 2 on x plus a constant. Again, let's go back to our initial conditions. When t equals 0, displacement was 1. This time I didn't get lucky. Constant's not 0. Constant is minus root 2. So there we are. But again, not quite what they asked for. I've got an equation for time in terms of displacement. They wanted an equation for displacement in terms of time. So we have to make x the subject of this. Now another way I could have got there was to use a definite integral rather than playing around with the constants. So I could have said t is the integral from 1 to x of x on minus 3 on 2. Okay? And then I'd sub in, and you'll see we actually get the same answer, although that one is factorised. Okay. I'm playing around with, remember we're trying to make x the subject. So I've got t plus root t is root t on x. So 2 on x is t plus root t all squared. Turn it upside down, would be x on 2, but then multiplying by 2. And there's my formula, 2 on t plus root 2 all squared. Let's do an HSC one then. Particle, again, moving along our x-axis, giving us some initial conditions. And the initial velocity, 5 meters per second. It's in terms of displacement. Show that the velocity is x squared plus 1. Okay, well, again, acceleration in terms of displacement. So I'm going to use d dx of half v squared. So half v squared, integrating. Got to find my constant. Initial conditions that link velocity and displacement. What was it? When x is 2, velocity is 5. Sub that in, my constant is a half. So I've also multiplied everything by 2, you'll notice, because the constant was a half. So I've ended up with v squared is x to the power of 4 plus 2x squared plus 1. V squared is x squared plus 1 all squared. So v squared is x plus 1. But hang on a sec, technically v squared is plus or minus x squared plus 1. So I really should mention something about why I chose the positive rather than the negative square root. I mean, why isn't it minus x squared minus 1? And again, that's to do with the initial conditions we have to satisfy. So note, velocity is greater than 0 in order to satisfy our initial conditions. Hence, find an expression for x in terms of t. So dx to t, so it's the same sort of idea as our last example. I'm going to do a definite, but I've actually put the integral of the t in there. So what I'm saying is you match your limits up. When t is 0, displacement was 2. And we're going to some random time and want to come up with an expression for displacement. So when we substitute t into t, okay, we get t. On the right-hand side, we've got an inverse tan function. So inverse tan of x minus inverse tan 2. Want to make x the subject. Inverse tan of x, t plus inverse tan 2. To undo the inverse tan, we tan. So tan t plus inverse tan 2. Of course, that's how mere mortals would leave it. Us super mathematicians. Well, it's the tan of alpha plus beta, so tan plus tan on 1 minus tan tan. Okay, so 3e.